So in this video we're going to be looking at two source interference and the diffraction grating. Now we'll start by looking at two source interference, and our two sources will be these two slits in an opaque piece of material. We will shine laser light onto them, and that will behave as our two sources of light. Why are we using laser light? Well, the laser light is coherent. What does coherent mean? Coherent means that the two sources are of the same frequency and they have a constant phase relationship. In other words, when they emerge through these slits here, they will be in phase with each other. Okay, so if we were to shine our coherent light onto our double slit, then we will end up with a pattern on the screen that looks a little bit like this. You'll end up with a big bright spot, and then you'll end up with more bright fringes as you move further away. Okay, so you end up with a pattern on the screen that looks a little bit like that. Now, this is an approximation of what you actually see, but for our purposes it should work out. Now, if I were to trace two rays from the two slits to this central maximum here, you end up with this. So I've got light ray 1 and I've got light ray 2. Now, if the two waves are coherent when they emerge through the slits, then they should arrive at the screen in phase, and because they arrive at the screen in phase, you get constructive interference and therefore a bright spot. Now, if we look at the second one out here, this second one here, if we trace our two rays again, then we will actually find that the bottom ray has travelled slightly further than the top ray. Now, if we were to zoom in a little bit here, then we can see that the extra distance travelled by the bottom ray is actually only this little bit here. Okay, so it's only a little bit further. If you zoom out, you can see that this is like an isosceles triangle, so these two lengths are actually the same, but the path difference is just this extra little bit here. So the bottom ray has travelled slightly further than the top ray by this amount here. If this amount here is one wavelength exactly, then they will still arrive at this screen in phase. And if they arrive at this screen in phase, we'll get constructive interference and a bright spot there. So this path difference here is equal to one wavelength. Now, if you were to look at a dark spot, for example here, then the path difference will be half a wavelength. If the path difference is half a wavelength, they will arrive at the screen antiphase. Antiphase meaning that they will arrive 180 degrees out of phase. So they will cancel each other out and you'll get complete destructive interference and therefore a dark spot on the screen. Right, so the diffraction grating then is very similar to two source interference, but instead of having a double slit like we did with the two source interference, we've got multiple slits, hundreds of slits, thousands of slits in a row that we will shine our laser light through to produce multiple sources of coherent light. Now, before we start, I will define our slit separation. So slit separation is the distance between the individual slits, and that's usually represented with lowercase d. Now, if I shine the laser light through without actually having without the diffraction grating, I should see a bright spot about there. Now, if I add the diffraction grating in, I get the same pattern as I did with the double slits, except instead of broad bright spots, I end up with very discrete, smaller bright spots, like so. If I were to look at the first bright spot in the middle here, this is our central maximum. Now, this is our zero order maximum, n equals 0, and then we have a first order maximum there, that will be n equals 1, a second order maximum where n equals 2, and you'll end up with the same underneath as well, n equals 1, n equals 2. In fact, you'll probably see more. You might see n equals 3, n equals 4, and so on and so on. Now, our angle between zero order and the first order is theta. And we can find angle theta using the following equation. D sine theta is equal to n, that is the order that you choose, lambda, or n times the wavelength. Okay, so for this particular angle theta here, we will use n equals 1. If we were to use this angle theta here for the second order, we'd use n equals 2, and so on. If you want to do the third one, you could do n equals 3, and so on and so on. This is particularly useful in astronomy. If you wanted to measure the specific wavelength coming from a star, you could use a diffraction grating and split it up, and you could see what angles they separate into, and you could find lambda, the wavelength, from that. Now, just one more thing. Now your slit separation, you might actually be told that your diffraction grating has, say, 300 lines per millimetre. And you could actually find the slit separation in millimetres from that just by doing 1/300. And that will give you the slit separation in millimetres. And that is diffraction grating and two-source interference. I'll see you in the next video.